It's invisible, it moves at thousands of meters per second, and it tells us the secrets hidden deep inside steel. This isn't science fiction, it's the science of sound, and how we use it to protect the world's strongest structures. In the world of structural inspection, sometimes the most powerful tool is one you can't see. Sound. Ultrasonic waves, sound vibrating at millions of times per second, have become the backbone of modern thickness measurement. These waves move faster than you can blink, yet they can uncover the tiniest changes inside a solid wall of steel. But how does it work? How can something you can't see or hear reveal the invisible, the hidden, and the potentially dangerous inside the things we rely on most? Let's break it down. A sound wave is a mechanical vibration, a pulse that travels through matter. Unlike light, sound can't travel through a vacuum. It needs a medium, D, whether a solid, a liquid, or a gas, to push through. The tighter the particles packed in that medium, the faster sound can travel. That's why sound moves much faster in steel than it does in water, and faster in water than in air. But in ultrasonic thickness inspection, we don't deal with the sounds you hear every day. We use ultrasound. Sound waves vibrating at frequencies above 20,000 Hz, far above what the human ear can detect. Most ultrasonic thickness gauges use sound in the range of 0.5 to 6 MHz. That's hundreds of times higher than the highest note you could ever hear. But why use such high frequencies? The answer comes down to precision and penetration. Here's the fundamental trade-off. High frequency means better resolution, but less penetration. Lower frequency means deeper penetration, but lower resolution. So, if you're inspecting thick steel, you need a lower frequency probe to push those waves deep inside. But if you're searching for fine cracks or tiny pits hidden just below the surface, you reach for higher frequencies. Another key factor is wavelength. Wavelength is simply the distance between two peaks in a wave. But here's the catch. If the flaw you're looking for is smaller than half the wavelength of your sound wave, you might not detect it at all. This is why selecting the right probe and the right frequency isn't just technical, it's absolutely critical in ultrasonic testing. Now, let's talk about the types of waves used in UT, or ultrasonic testing. There are two main kinds, longitudinal waves and shear waves. Longitudinal waves, also called compression waves, are the workhorses of most ultrasonic thickness gauges. In these waves, the particles of the material vibrate parallel to the direction the wave is moving. They travel fast, and they're particularly good for measuring thickness or detecting deep flaws in solid metals. Shear waves, on the other hand, are different. Here, the particles vibrate perpendicular to the direction of the wave. Shear waves move slower than longitudinal waves, but they're especially useful for revealing defects like cracks in welds, because they're more sensitive to changes in the structure of the metal. But there's a catch. Shear waves can't travel through liquids. That's why you'll find them used mostly in dry surface inspections, not underwater. Every material resists the passage of sound to a different degree. This resistance is called acoustic impedance. When a sound wave traveling through steel hits a boundary, like the back wall of the metal or a hidden pocket of rust, part of that wave bounces back as an echo. That echo is the signal we measure. The greater the difference in acoustic impedance between two materials, the stronger the reflection. That's why when a sound wave goes from steel to air, you get a crystal clear echo. If it goes from steel to rust, the echo is weaker and harder to interpret. Knowing how waves reflect, or refract, at boundaries helps us interpret the signals we see on the screen. Sound doesn't always travel in straight lines. When a wave hits a new material at an angle, it bends, just like light bends when it passes through water. This bending is called refraction, and it's explained by Snell's law, a fundamental principle in physics. Understanding refraction is essential when using angle beam probes, especially when you're sending shear waves into welds to hunt down flaws. If the angle is off, the echo might never come back to you, and you'll miss the defect entirely. This is why precise control, calibration, and experience are vital in ultrasonic inspection. As sound travels through a material, some of its energy gets absorbed or scattered. This gradual loss of signal strength is called attenuation. Coarse-grained materials like cast iron or stainless steel absorb sound waves much faster than fine-grained materials. So do corroded surfaces, paint layers, or dirty coatings. That's why surface preparation, proper coupling, and the right gain settings are so important when measuring with ultrasound. If your signal fades too much before it even reaches a flaw, that flaw won't echo back, and you'll miss a critical sign of weakness. In ultrasonic testing, every reading, every echo, depends on understanding how sound behaves inside metal. What kind of wave are you sending? How fast is it traveling through that particular alloy? What's happening when it hits each boundary? And when it finally comes back, what does that echo mean? Ultrasonic testing isn't just about numbers on a screen. It's about reading the language of sound. Sound waves let us see what our eyes never could. A single, well-placed pulse can reveal thinning caused by corrosion, hidden cracks inside welds, and even invisible manufacturing flaws that could threaten the integrity of a structure. Let's follow the journey of a sound wave as it moves through steel. Imagine you're holding a UT probe against the surface of a massive steel bridge support. You press the probe down, and a thin film of gel ensures perfect contact. The probe emits a short, powerful pulse of ultrasound. That pulse travels into the steel at over 5,900 meters per second. As it passes through the steel, it encounters boundaries: the back wall, a possible air pocket, a patch of rust. Each time it hits a boundary, some of the sound is reflected back to the probe as an echo. The ultrasonic instrument measures the time it takes for the echo to return. Because the speed of sound in steel is precisely known, the time delay tells you the exact thickness of the steel at that point. If the echo comes back sooner than expected, it means the steel is thinner, perhaps corroded. If the echo is delayed, maybe there's a patch or repair. If you see more than one echo, it could mean there's a flaw or a pocket of rust inside. By systematically scanning a structure, inspectors can create a complete map of thickness and detect dangerous weaknesses, all without ever cutting or damaging the material. This is why ultrasonic thickness measurement is so powerful. It's fast, accurate, and non-destructive. But ultrasonic testing is more than just pressing a button. It's about understanding the science behind the signals. The choice of probe, frequency, and wave type all matter. For thick, dense metals, a lower frequency probe is best because it penetrates deeper. For thin materials or fine flaws, a higher frequency probe gives sharper images. The coupling gel is essential to ensure sound passes cleanly from the probe into the metal. The gain settings on the instrument must be adjusted to amplify weak echoes without creating too much noise. Experienced inspectors learn to recognize the subtle differences between echoes. A sharp, strong echo from the back wall means solid, healthy steel. A weak, fuzzy echo could mean corrosion, pitting, or even a hidden crack. Patterns of multiple echoes might reveal laminations or delaminations inside the metal. It's not just about finding flaws, though. Ultrasonic testing also helps monitor known issues over time. By regularly measuring thickness at critical points, inspectors can track how fast corrosion is eating away at a structure. This data helps engineers make informed decisions about maintenance, repair, or replacement before a failure occurs. Ultrasonic waves also help us understand the quality of welds. In welded structures, from pipelines to ship hulls to skyscrapers, hidden cracks or voids can be catastrophic. Using angle beam probes, inspectors send shear waves into the weld at carefully calculated angles. The echoes that return reveal the presence, size, and location of flaws. Careful mapping and interpretation of these signals help ensure the strength and safety of vital connections. The magic of ultrasonic testing rests on the physics of sound. It's a dance of waves and echoes, of energy and boundaries. Every reading tells a story, if you know how to listen. But ultrasonic testing isn't without its challenges. Surface conditions matter. Rough, dirty, or painted surfaces can scatter or absorb sound, making echoes harder to interpret. Temperature changes can affect the speed of sound in metal, requiring careful calibration. Complex shapes, like curved pipes or irregular welds, demand skillful probe placement and angle adjustment. Despite these challenges, ultrasonic testing remains one of the most versatile and reliable tools for safeguarding our infrastructure. From bridges and ships to oil rigs and power plants, the silent pulse of ultrasound is at work every day, revealing the unseen, protecting the strong, and ensuring safety. In the end, ultrasonic thickness measurement is about more than just measuring metal. It's about trust. It's about knowing that the bridge you drive across, the airplane you fly in, and the factory that powers your city are all safe, sound, and ready for the future. Because once you understand how sound waves reveal what you can't see, you're no longer just measuring thickness, you're measuring integrity. In our next exploration, we'll dive into the tools of the trade, the probes, the gauges, and what makes each one right for the job. We'll break down the difference between single and twin crystal probes, the power of angle beam applications, how to match frequency to material, and the vital role of calibration blocks in keeping your readings sharp and reliable. So, if you've ever wondered how we make steel, speak. Stay tuned, share your thoughts, and join us as we continue our journey into the world of ultrasonic testing. This is Understanding UT, and we're just getting started.